notice that's different. I go back 2 slides. What I had before. Before it dropped down to 1321. When I added male, PAX1, PAX2, and PAX3. Now when I add male and the continuous variable, drops, oops, my machine's acting up. It dropped down to 1324. That's a drop not of 29 points, of 26 points of the fit of this model, the model with male and PAX, versus the model with just the intercept. That 26-point drop corresponding to a p-value less than 0.0001. But notice now we only have 2 degrees of freedom for this test, because the difference between the intercept-only model and the intercept plus covariates model was looking at a model with just the B0 term to the model with the B0 plus male plus PAX added to it. And that added a B1 term and a B2 term. That's why we have only 2 degrees of freedom. We'll get back in a second to try and decide which is the better of these 2 models for our purposes, the control confounding, and look at the effective male. But let's look to see what this model gives us for the effective male. Here's our fitted model. The coefficient, or the estimate for B0 is minus 1.79. The estimate for B1, coefficient of male, is 0.68. The estimate for PAX is 0.04. If we're focusing on the coefficient of male, we want to know what the effect of male sex is on your risk of developing heart disease, controlling for smoking. The 0.6838 is what we'll be focusing on. We can look at its standard error, divide the coefficient by the standard error, and square it. You get a chi-squared test of 21, and a p again less than 0.001, saying controlling for smoking in this model as a continuous variable gives me a significant coefficient of male. That corresponds to an odds ratio of 1.98, very similar to what we had before. So for purposes of looking at the adjusted effect of sex on your risk of developing heart disease, these 2 models gives us very similar odds ratios, very similar adjusted odds ratio. 1.98 in this model, to control for smoking as a categorical variable, was 1.97. Very, very similar. But the question I think you should be asking yourselves is which of these 2 models is better? Well, we need a way to measure what better means. How do we decide which of 2 models that we might be considering as our final model is the better model? And I'm going to just talk today about 2 options. We're trying to decide which is better. One model is to look at one option is to look at the value for minus 2 log L. Go back 2 slides. Remember, the L means the likelihood. We want a likelihood from a model to be close to 1. A good fitting model will give us risk estimates that are close to 1 for people who got the disease, risk estimates for P which are close to 0 for people who didn't get the disease. So we want our P's to be close to 1 for people who got the disease. We want our P's to be close to 0 for people who didn't get the disease. Now remember, the likelihood is a bunch of P's multiplied by a bunch of 1 minus P's. P's for people who got the disease, 1 minus P's for people who didn't get the disease. We want the likelihood to be close to 1. We want the log likelihood to be close to 0. So all things being equal, we want the minus 2 log L's for the model with the intercept and the covariates to be small. We want it to be close to 0. So all things being considered, smaller is better for value for minus 2 log L. Well, the value for the minus 2 log L for the model with male in PAX1, PAX2, and PAX3 was 1321. The model with male in PAX was 1324. So the smaller value was for the model with male, PAX1, PAX2, and PAX3. That gave us the value of 1321. So all things being considered, the first model was fitting the data set better than the second. Well, there's another problem, though, with model fitting. The more terms you add to a model, the smaller the minus 2 log L will become. So and that means bigger models are always going to be better than smaller models, because bigger models are going to be more complex. They're going to add more flexibility to a model's ability to fit a data set. So that means if we go by the first option, saying let's go with the model with the smallest value for minus 2 log L, what that usually means is we're going to end up with very, very big models. big models might not necessarily be the best models, especially if you're trying to build prediction rules. This is not what we're talking about right now, but let's imagine we want to build a model that could predict a person's risk of developing heart disease. We want to include in that model all the important risk factors. Well, if we fit such a model, we'll see a model in a few minutes that has a lot of risk factors in it. Right now, we're just seeing models with gender and smoking in it. But let's suppose we added to the model other factors like blood pressure and cholesterol levels and age of the individual. We might end up with a model that we could use to predict a person's risk of developing heart disease in the next 18 years. That might be very useful for a doctor, because if I'm seeing a patient and that model tells me this patient has high risk of developing heart disease in the next 18 years, I might try to introduce some interventions into that person's lifestyle to lower his blood pressure, to lower his cholesterol levels. I can't change his gender, I can't change his age, but I can change some of his risk factors. So a prediction model, a model that assigns risk estimates to people, is a very good rule. We would like a model that predicts well, but remember, smaller is always going to be better if you go as -2 log L as a judge for what a good model is. And I also said that in general, the bigger the model is, the more complex the model is, the smaller the -2 log L will be. I start adding other factors to my prediction rate, other factors that really are not true risk factors, but are just quirks in this one data set. Maybe in this data set, people who lived on the right-hand side of the street were more likely to develop heart disease than people who lived on the left-hand side of the street. Not because living on the side of the street reflects your risk, but just maybe by chance alone in these data sets, the side of the street was related to your risk of getting heart disease. But it won't be related in other data sets. So chances are it's not a true risk factor. Chances are I do not want to include it in my model. But by doing so, my -2 log L gets smaller. And that's the problem. Bigger models would tend to work better than smaller models, because bigger models, I mean models with more risk factors and models with other factors, that just by chance are related to the outcome in this data set, are going to give you smaller values or -2 log L. So how do we guard against not always going with bigger and more complex models? How do we give the smaller models, which work almost as well in this data set, a fighting chance of being the best model for this data set? Well, one way of doing that is to penalize the -2 log L for the size of the model. There's something called the AIC. A stands for a Japanese statistician's last name. Akiyeki, I believe, is the pronunciation of it. I suspect some of you know how to pronounce Japanese names better than I do. But Akiyeki was the statistician who proposed the following rule for trying to decide how well one model fits the data set compared to another. Akiyeki says, take the -2 log L, but add to it a number of points. Add 2 points for every regression coefficient we want to estimate. So if I'm just estimating a model with the intercept only, I'm going to take the -2 log L and add a 2 to it, because I have to estimate a B0. If I'm estimating in the last model we look at, a B1 for the coefficient of male, a B2 for the coefficient of packs, I'm going to end up estimating 3 coefficients, B0, B1, and B2. That means I'm going to add 6 points to the value for -2 log L. So bigger models get penalized more because bigger models have more coefficients that have to be estimated. So when we looked at the model with male, PAX1, PAX2, and PAX3, let me go back to that model. The -2 log L for the intercept plus covariance of 1321. The value for the AIC is 10 points higher than that. It's 1331. The reason it's 10 points higher is because there are 5 coefficients in this model that have to be estimated. Now, Akiyeki says the penalty should be 2 points for every coefficient you're estimating. So the 1321 for the -2 log L becomes a 1331 for the AIC statistic. And the model with male and PAX had a bigger value for -2 log L, 1324. Now it has a value for the AIC of only 6 points higher, because I only have to estimate 3 coefficients. So maybe a better way to decide which model is better is not to look at the model with the smallest minus 2 log L. Look for the model with the smallest AIC statistic. For the model with PAX1, PAX2, and PAX3 plus male, it was 1331.